This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 26, Computational Chemistry. There are three categories of methods in computational chemistry: ab initio methods, semi-empirical methods, and molecular mechanics. First, ab initio methods. Ab initio means from the beginning, or first principle. The ab initio methods solve the Schrödinger equations without using any empirical parameters from any experiments. The ab initio methods are often accurate but very slow, with one exception. That's the Hartree-Fock theory, or the Hartree-Fock method is often inaccurate. This is because in the Hartree-Fock theory, the electron-electron repulsion is approximated by averaging over many other degrees of freedom. For example, if you try to calculate a molecule with 100 electrons, supposedly you need to solve one single Schrödinger equation for this 100 electrons. But in Hartree-Fock theory, you solve 100 Schrödinger equations. Each contains only one electron. But how can you approximate the repulsion each electron feels? Very simple. Electron 1 feels repulsion from electron 2, electron 3, electron 4, all the way to electron 100, right? So we can put those repulsion terms together and integrate all these repulsion terms with respect to the coordinates of electron 2, electron 3, and all the way to electron 100. And then we simplify this repulsion terms to one electron repulsion operator. And this is a very inaccurate description of the electron repulsion. So the Hartree-Fock energy calculated with the Hartree-Fock method is often much higher than the exact energy of the molecule. The difference between the Hartree-Fock energy and the exact energy is the so-called correlation energy. So there are so many post-Hartree-Fock theory that includes the correlation energy in different ways. There are configuration interaction theory, such as CISD method, molar placid perturbation theory, such as the MP2 method, MP3, MP4 methods, the density functional theory, such as the B3LYP method. This is a very popular DFT methods, and also one of the most criticized method, because many people use this method without seriously verifying the accuracy of this method for their systems. There's also a so-called coupled cluster theory, which is really accurate, but the computational cost is extremely high. So to get reasonable results, we usually use the density functional theory method, or the DFT method, to achieve the balance between efficiency and accuracy. If you want really good accuracy, you can consider using CISD to get your result. When we conduct a ab initio calculation, we have to choose one of these methods: Hartree-Fock, CISD, MP2, B3LYP, CCSD. And also, we need to choose a basis set for the system. The basis set provides pre-parameterized mathematical functions, usually Gaussian functions. But you can also use sine functions, cosine functions, exponential functions, whatever mathematical functions that are smooth and finite to describe the atomic or molecular orbitals of your system. All right? This is very important. The second category, semi-empirical methods. Semi-empirical methods are similar to the Hartree-Fock methods. It's just in the Hartree-Fock calculations, we need to calculate many integrals. and that's very tedious and very time-consuming. So in the semi-empirical calculations, we neglect some of these small integrals. We estimate some significant and important integrals. Because of those neglection, estimation, semi-empirical methods sometimes are less accurate than the Hartree-Fock method and less accurate than the post-Hartree-Fock methods. The advantage of using semi-empirical method is this. It's really fast. It's faster than the Hartree-Fock method because, again, the semi-empirical calculations neglect many integral calculations. There are exceptions. Sometimes semi-empirical methods are much more accurate than the Hartree-Fock method because when we parameterize this semi-empirical methods such as AM1, PM3, PM6, those parameters are obtained by fitting the method to the prediction of the method to the experimental value of some training compounds. So that means if you are using a semi-empirical method to calculate one of its training compounds, well, you'll get very accurate result. Or if you're doing semi-empirical calculations for similar compounds, similar to the training compounds, I think you'll get pretty accurate results, more accurate than the Hartree-Fock method, comparable to, for example, the density functional theory, or even couple cluster. Okay, and again, semi-empirical methods are much faster than the initial methods, and typically they are less accurate, with some exceptions, especially for the calculation of the training compounds or similar compounds. Molecular mechanical methods. This is in the realm of molecular mechanics. This kind of methods do not solve the Schrödinger equations at all. So this kind of methods are often less accurate, but faster than the semi-empirical methods. So when we use molecular mechanical methods, we treat each atom as a sphere, like in classical physics. Each bond like a spring. And we allow the bond angle to change. So for example, in water, we allow this HOH bond angle to change by imagining putting another spring between the two OH bonds. So in this case, this molecular mechanics uses Newtonian mechanics to model the molecular systems. So again, we do not describe electrons as waves. There are no electrons in molecular mechanics. We just look at those atoms. And the potential energy of all systems in molecular mechanics is calculated using force fields. A force field is just a set of parameters used to estimate the energy of a bond when it's stretched or when it's compressed in comparison to its equilibrium bond distance. So when you do molecular mechanical calculation for a molecule at its equilibrium geometry, the energy is just zero. So if you stretch a bond or compress a bond in water, and then you'll get positive energy compared with the equilibrium geometry of water. Molecular mechanics can be used to study very large biological system because it's really, really fast. It can be used to calculate a system of thousands or even millions of atoms. So again, in summary, in molecular mechanics, each atom is simulated as a single particle or just a sphere. Each particle is assigned a radius. For example, Van der Waals radius. Each particle is assigned a polarizability because we can then calculate the interaction between the induced dipole and dipole moment, and a constant net charge when there is a charge or partial charge. For example, if you have a bunch of HCl molecules and then we assign partial positive charge to the hydrogen atom and a partial negative charge on the chlorine atoms. The bonding interactions again are treated just as springs, not just the bonds, but the bond angles. The change of the bond angles are also treated like the stretch of springs as well. And sometimes we use a so-called hybrid method, such as QMMM, to calculate a fairly large system. The idea is this: we use the quantum mechanical method or ab initio method to look at a small region, the most important region, okay, with accurate ab initio methods. Okay, we use wave functions to describe electrons. But then there's a supporting region, and then we use molecular mechanics to describe the supporting region, the last important region. Right? So maybe this region contains maybe 100 atoms, and then the molecular mechanics region contains 1 million atoms. So this way we can balance the accuracy and efficiency. So over here, it's just a random example I got from the internet. We can use a fairly accurate ab initio method to describe, this molecule. Just imagine this is a drug molecule interacting with a enzyme, I guess. And then the ribbons contains thousands or millions of atoms that can be described by molecular mechanics. And then this whole structure is in water. Can you see all those small water molecules? These water molecules or any other solvent molecules can also be modeled by the molecular mechanical methods. So this way we achieve accuracy and efficiency at the same time.